We're at a point in this course, Differential Equations and Linear Algebra, where the differential equation and linear algebra content seem very far apart. Okay? And that's just the nature of the beast at the moment. They will come back together. I'm hoping starting about 5, 6, 7 lectures from now, the topics will start to merge back together to some degree. We'll see that it really does make sense to put them together in one course. But at the moment, it feels like 2 courses. Lecture 8b is about 3-dimensional linear algebra. In lecture 7b, we actually did higher dimensions. We talked about matrix vector multiplication in general with an m by n matrix times an n by 1 vector, giving you an m by 1 vector. But now we want to go back to 3 dimensions, I think, for this lecture and the next lecture, because there's some concrete things that we need to think about that would be beneficial to know before we go on and get more abstract again. So we're going to focus on 3 dimensions: vectors, 3-dimensional space, linear transformations, matrices, elementary row operations, row echelon forms, parametric vector forms of solution sets. That sounds like it would be too much to cover in such a short time, but if we think about these things in the context of an example, I think it will go pretty quickly here. And so here is our example. A flow network to model, for example, traffic flow. And our goals are to find the values of some unknowns to balance the following network. Here is our network. So we're trying to solve for x, y, and z. Solving equations, linear equations, is the foundation of linear algebra, but then we have all these other things: vectors, matrices, row operations, thinking about things higher dimensionally that come into play, linear transformations as well, that are essential to the course. What does it mean to balance this? Well, evidently these are a bunch of one-way streets. The arrow indicates the street direction. These are arrows, you might say they're vectors, but I actually don't really intend them to be vectors in the usual sense. You could make these streets curvy if you want. They could be curvy in real life. A, B, and C are all intersections. What would it mean to balance? Well, what do these numbers mean? These numbers represent traffic flow, maybe a certain number of cars per minute or something, or per hour in this traffic network. Let's go ahead and pretend per hour. Let's say 20 vehicles per hour are traveling this direction along this stretch of this one-way road, 80 vehicles per hour here, 60 per hour over here. For these other 3, it's x, y, and z per hour. It should make sense to solve for x, y, and z in such a way that it all jives together, it all balances. We must solve a system of linear equations and 3 unknowns to do that. Here it is. What does that mean? We want, at each node, we want the inflow to equal the outflow. At node A, B, and C, what's the inflow and what's the outflow? Easiest to think of this in terms of traffic, but it has other applications, maybe to fluid flow. Maybe these are pipes, for example. At A, right here, the inflow is x plus y, right? Because you've got 2 streets, one-way streets going into A. The outflow is 20. And these must equal each other. That's what it means to balance at node A, intersection A. At node B, the inflow is 80, and the outflow is y plus z. We want those to be equal too. And at node C, the inflow is just z, and the outflow is x plus 60. So there is a system of 3 linear equations and 3 unknowns, x, y, and z. We'd like to solve for x, y, and z to figure out the traffic flow. Is there guaranteed to be a unique solution? This harkens back to lecture 8a with differential equations. No. In fact, in this example, it turns out there's not a unique solution. There are various things that x, y, and z can be. Here's another way to rewrite this system. So the first equation here is the same as the first equation there. These 2 are the same. This one here is the same as this one, except just switching around what's on what side. And the last one here I wrote differently. Effectively, I subtracted z from both sides and subtracted 60 from both sides and then swapped the direction to get the last equation, x minus z equals negative 60. And I'm purposely putting space, like you see here, in this system of three equations and three unknowns to line up the x's, y's, and z's, because that's going to correspond to using a matrix to help me solve this. That's what I'm about to show you. Using something called the row reduction algorithm on the corresponding augmented matrix. So again, we talked about matrices in lecture 7b. It's an array of numbers, a certain number of rows, a certain number of columns. That's going to happen here again. But this is not a matrix for a linear transformation, at least we're not thinking of it that way initially. It's a matrix whose entries are the coefficients in the system that I showed you in the bottom right corner. When solving the system via elimination, which is effectively trying to eliminate variables as you go, we talked about that when we talked about solving 2x2 systems, we can just focus on the coefficients. The x, y, and z, and then the constants on the right are just sort of placeholders in a sense. We don't really need them when we think about doing elimination. We can put these coefficients in an augmented matrix. It's called augmented because we're going to add a column for the numbers that are on the right-hand sides of the equations. And do what are called elementary row operations, which I'll describe as we go, to relate the original system to a reduced system that is easier to solve. Find an equivalent, simpler system that is easier to solve. And this is called the row reduction algorithm. It's a process for helping solve. So here is the starting augmented matrix. And I like putting vertical dashed lines in my augmented matrices by hand to separate the coefficients of the x, y, and z left-hand sides with the numbers that were on the right-hand sides. 20, 80, negative 60 were on the right-hand sides of that last system on the previous slide. The first equation in that last system was x plus y equals 20. You could draw equal signs in here too, perhaps, but I don't do that. X plus y equals 20. This corresponds to y plus z equals 80. 0 times x is just 0. You can just write y plus z equals 80. Here it was 0 times z. And the last equation was x minus z equals negative 60. We're trying to get this into something called reduced row echelon form, where we have some leading ones along the diagonal. Now we already have, the main diagonal of this is this thing right here. We already have a couple leading ones there. We don't have a leading one there. And we don't want this leading one over here to be under this one. We want all the quantities underneath the leading ones here to be 0, because that corresponds to eliminating variables. For example, if I do the following row operation, multiply row 1 by negative 1, that's why there's a negative sign there, add it to row 3 and put the answer in row 3, that's called a row replacement operation. That corresponds to, in the original system, multiplying the first equation by negative 1, adding it to the third equation, and putting the new third equation in your system. Let me go back over here. Here's the system I'm talking about. I'd like to eliminate that x. I could do that by multiplying this first equation, everything by negative 1, to get negative x minus y equals negative 20, adding that equation to this third equation to cancel the x's. Negative x plus x is 0. But I would get a negative y and a minus z, and then I get negative 20 minus 60 is negative 80. So I've eliminated the x's and I've introduced a y, but I've done a step of getting a 0 underneath this leading one down there. I want to make that thing 0, which again corresponds to eliminating the x. Here's the result. So you leave the first row the same, leave the second row the same, change the third row. That's what this notation means. Multiply row 1 by negative 1, add it to row 3, put the answer in row 3. Again, negative 1 plus 1 is 0, put a 0 there. Negative 1 plus 0 is negative 1, put a negative 1 right there. Following with me? 0 times negative 1 is still 0, plus negative 1 is negative 1. That stays a negative 1. 20 times negative 1 is negative 20. Negative 20 plus negative 60 is negative 80. Just like I said a minute ago, that y minus z, or negative y minus z equals negative 80. The new equivalent last equation. Now this augmented matrix is not much simpler. The main benefit of the algorithm, this process, is we've got a 0 in the lower left-hand corner, and we haven't done anything to this row, so this 0 stays as is, the second row, the first entry in the second row. So I've got two leading ones. This one has all zeros below it. This one along this main diagonal does not have a 0 below it. So the next step in the algorithm is to make that a 0. How? By doing another row operation. Take row 2, add it to row 3, put the answer in row 3. 1 plus negative 1 is 0. That will give me a 0 down there. That corresponds to, y times negative 1, or excuse me, y plus negative y is 0. If I was thinking in terms of the actual equations themselves. Here's the result. Taking row 2 and adding it to row 3 and putting the answer in row 3. 0 plus 0 is 0, so this stays a 0. 1 plus negative 1 is 0, so this becomes a 0. 1 plus negative 1 is 0, so this becomes a 0. And 80 plus negative 80 is 0, so this becomes a 0. Got a row of zeros there, so we can't possibly getting a leading one here. That's okay, that happens sometimes, as long as we are following this process here. Essentially, now what has happened is the last equivalent equation is 0 equals 0, and that doesn't tell us any new information, but it doesn't hurt, it's still true, 0 does equal 0. So now I can just focus on the first two rows. And again, I have these leading ones along the main diagonal, which are good. To get into what's called, again, reduced row echelon form, I need to get the zeros above leading ones as well. Now this one, leading one, doesn't have anything above it, so you don't need to do anything with that. But this leading one does not have a 0 above it. The next step in the algorithm is to make that a 0. So I'm going to multiply this row by negative 1, add it to this row, and put the answer in this row to make it 0 right there. That's the goal. And that's what I do here. Negative R2 is multiplying row 2 by negative 1, adding it to row 1, putting the answer in row 1. Negative 1 times 0 is still 0, plus 1 is 1, so that stays a 1. 1 times negative 1 is negative 1, plus 1 is 0, so this becomes a 0. 1 times negative 1 is negative 1, plus 0 is negative 1, make that a negative 1. 80 times negative 1 is negative 80, plus 20 is negative 60, make that a negative 60. And now I'm to the point where I am in reduced row echelon form. I've got these leading ones, and I've got a row of zeros. That's not a big deal. That doesn't always happen. Sometimes you get a 1 right there. In fact, it's the fact that this is all zeros that makes the solution set infinite. Infinitely many solutions, more than 1 for sure. And this is a simpler system, because this corresponds to x minus z equals negative 60. This corresponds to y plus z equals 80. I can solve for x and y in terms of z. And that's what I do. The reduced row echelon form of the augmented matrix is equivalent to the following system. The one I just said. X minus z equals negative 60. Y plus z equals 80. And 0 equals 0, which I can just get rid of. I can ignore that because I know that's true. I don't need it. I can add z to both sides of the first equation and subtract z from both sides of this equation to write both x and y as functions of z. And for this kind of problem, that's the way you want to write the answer. And that does emphasize that there are infinitely many answers, because z can be anything. There are infinitely many different traffic flows in that diagram that make the flow balance, make the network balance. Although, in terms of the real-life application, x, y, and z have to be non-negative. Z would have to be greater than or equal to 60 to make x greater than or equal to 0, and in fact less than or equal to 80 to make y greater than or equal to 0. So, even though that's the solution, z would have to be between 60 and 80 for the application. As far as the system itself goes, the abstract mathematical system itself doesn't care about the application. You can solve such a system without thinking about any applications. And so then z could be anything. But as far as the applications go to the flow network, you need this to be true in order for x and y to both be positive, greater than or equal to 0, non-negative, is what I should say. This kind of system of equations should kind of feel familiar. I mean, what if I used a t instead of a z? What would that be? That would be a system of parametric equations. And it would define a parametric curve in the xy plane, or if I allowed z to be visualized as part of the picture, I could add a third dimension, and this would be a line in three-dimensional space. It would be the set of all points. I'm specifically writing points here instead of vectors. Where the x-coordinate is z minus 60, the y-coordinate is 80 minus z, and the z-coordinate is z, such that z varies over the real numbers. This is going to be a subset of the three-dimensional space, because these are three-dimensional points here. So I'm doing something a little different than what you typically do with parametric equations in this situation. I'm adding a third dimension. This describes a parametric curve in three-dimensional space, which will be a straight line because these are linear equations in z. Z is just the first power. You do see constants in there, and you might wonder, does that contradict the idea of a linear transformation, not including constants? The answer is no, it doesn't contradict that. I'm thinking of this as something different than linear transformations. And so I'm allowing constants, the negative 60 and the 80, to be in there. This parametric description is not unique. You actually can redo the algorithms so that you solve, for example, for y and z in terms of x, for example, or x and z in terms of y. And you'd get different parametric descriptions of the solution set. So it's not unique. There's not a unique answer. But based on the row reduction algorithm, this would be the one you'd come up with. We can also think of these solutions as being vectors. And it's worthwhile to think of it both ways. We want to be flexible. So I'm writing the solution set as a set of vectors in this situation now. Z minus 60, 80 minus z, and z, as z varies over R, as a subset of three-dimensional space as well. But wait a minute, are the elements of three-dimensional space, are they points or are they vectors? You can think of it either way, and you can relate the two by the natural correspondence we've talked about. By rules for vector addition and scalar multiplication, and z is a scalar here, I can rewrite this kind of vector in this way. This is called parametric vector form. It's a common way to write the solution set. If that's not clear how to do that, I was essentially separating the constants negative 60, 80, and 0 from the z terms, z, negative z, and z, to get two different vectors. And then with this one, which I would have had z, negative z, and z initially, I factored out the scalar z to write this as parametric vector form. Writing it in this way has the benefit of that it helps you graph it the easiest. Effectively, we're going to graph it as a set of points, but these vectors help you figure out what that set of points is. Essentially, this vector, negative 60, 80, 0, which is constant, so to speak, is if you draw the tail of the vector at the origin, its tip will be on the line that is the set of points that solve the system. And this vector here, next to the z, 1, negative 1, 1, is parallel to the line. Not going to get into details because it would take too long, but essentially this is the definition, the geometric definition of vector addition based on the head-to-tail definition. You could also think of it in terms of the parallelogram rule. Here's the picture that I had Mathematica draw. This blue vector right here is the vector negative 60, 80, 0. Its x component is negative 60. Here's the x-axis kind of coming out of the screen at you. That's the positive direction. The negative direction is back behind the screen. So this blue arrow is effectively behind the screen. It's behind the YZ plane. It's not technically the screen because I've slanted it a bit, but you get the idea. Its y component is 80. It's going in the positive y direction, which is to the right. And its z component is 0. It lies in the xy plane. The xy plane goes about like this. this is lying in that plane. Try to draw it, that's what you want to imagine. The black vector is too long to be 1, negative 1, 1, but it's parallel to it. Parallel to 1, negative 1, 1. I'll let you think about that. It's some multiple of that vector. Z is some positive constant here to make that black vector. Right? Think about it, Z times 1, negative 1, 1. The red points is the solution set as a set of points. And it's a line, straight. And it is the intersection of three planes. And the original system of equations defines three planes. Those planes, in general, with three equations and three unknowns, will typically intersect at just one point. However, in this example, they happen to intersect along the line. It doesn't typically happen in such a situation like this. I'll let you think about it to see if those seem reasonable as graphs of the original system of equations. By the way, in lecture 9b, we're going to talk about how to graph planes as well. I'm going to talk about something called the cross product. Yeah, each of the three equations in the original system defines a plane. We'll talk about why in lecture 9b. The solution set is the intersection of those three planes like you see. All right, take a breath. Gotta go a little faster here, thinking. Thinking in terms of vectors and linear transformations, using the definition of vector addition and scalar multiplication, the original system can also be thought of as a linear combination of vectors. Do you remember that from lecture 7b? We talked about matrix vector multiplication in terms of linear combinations of the columns of the matrix, where the entries of the vector were the weights. And that can be brought to bear here. I can think of this system of three scalar equations and three unknowns x, y, and z as being an equality between two vectors, a vector equation. One vector equation instead of three separate scalar equations, though I still have three unknowns for the components of the vector as part of the components. And this thing can be broken apart like this, as a linear combination. Here's the linear combination. A scalar times one vector plus a scalar times another vector plus a scalar times another vector. That's called a linear combination. How did I get these vectors? Well, the x terms are here and here. There's no x term there. The coefficients of x are 1, 0, 1. That's where this vector comes from, 1, 0, 1. For y, the coefficients are 1, 1, 0, 1, 1, 0. And for z, the coefficients are 0, 1, negative 1, 0, 1, negative 1. We are still looking for the same thing, the scalar values, x, y, and z, that make this equation true. But being a linear combination like this, I can relate it to matrix multiplication. As we saw in lecture 7b, this can be thought of in terms of matrix vector multiplication like this, where this matrix, let's call it capital A. And we could call this vector boldface x, or x with a half arrow, say. And we could give this vector name as well, and in fact I do, I'd call it B. What did we talk about in 7b? A matrix times a vector, like this, a 3 by 3 matrix in this case times a 3 by 1 vector, is a linear combination of the columns of the matrix, where the entries of the vectors are the weights or coefficients. So we have x times the first column, that's this, y times the second column, that's that, z times the third column, that's that. And this can be shorthanded to ax equals b. And it can be related to linear transformations. In this case, from R3 to R3. This vector is three-dimensional, the input vector, so to speak, and the output vector is three-dimensional, R3 to R3. Defined by t of x equals a times x. And as emphasized in lecture 7b, this is t of x, that's function notation, say the word of. This is a times x, that's a matrix times a vector, say the word times. But this is an equation that defines the linear transformation. Studying the linear transformation, we can ask and try to answer other questions about the linear transformation, this function capital T. that we did look at some in 7b. We could say, is it 1 to 1? For each output, was there a unique input that got mapped to it? Another way to say that is if you got two distinct inputs, do they get mapped to different outputs? If that's true, then we say t is 1 to 1. Another name for 1 to 1 is injective. I'm just mentioning that here. I don't know if I'll mention it again. Maybe I will. It's also important when thinking about whether t is 1 to 1 to also ask what set of points get mapped to the zero vector. This is called the kernel of t. And for the matrix A, it's also called the null space of A. All the vectors, the set of points or vectors, slash vectors, because I can think of them either way, that get mapped to the zero vector in the output space. Both the inputs and outputs are three-dimensional here. In general, they don't have to be the same dimension. Again, this is called the kernel, this set. Here's a way to write it in set builder notation. The kernel of t, shorthanded ker t, is the set of all x in R3 in this example, thinking of that as the input space. If our matrix was m by n, m rows, n columns, the domain would be Rn, n-dimensional space, and the codomain would be Rm, m-dimensional space. And this would be an n here. The domain is n-dimensional in that case. But here in this situation, both the domain and codomain are three-dimensional. Set of all points in the domain that get mapped to the zero vector in the codomain. That's going to be a subset of the domain. This is subset of that. I think I mentioned that before. If t is 1 to 1, it's going to turn out that the kernel is just the zero vector in the domain. Certainly the zero vector does get mapped to the zero vector. Certainly A times the zero vector is the zero vector. You plug in the 0 into the x, y, and z and do the multiplication, you're going to get a linear combination where all the weights are 0. You'll get the zero vector out. So certainly the zero vector is in the kernel. This happens with linear transformations when you don't do any adding constants. It does not happen in general for nonlinear transformations. And in fact, because t is 1 to 1, that's the only possibility. There can't be any other vectors in the kernel. On the other hand, if t is not 1 to 1, you might think that's not a guarantee that the kernel includes other non-zero vectors, but it actually will with linear transformations. Is t onto? That's also called surjective. Given a point in the codomain, is there something in the domain that gets mapped to it? Give me any arbitrary point in the codomain. Can I find something in the domain that gets mapped to it under t? Also called surjective. In other words, what is the image of t? Is it all of R3 in the codomain? If it is, then it'll be onto. If it's not, then it's not onto. Here is again the definition of the image. The set of all t of x's as x ranges over the domain. And you want to think of this as a subset of the codomain. Though again, the domain and codomain in this example happen to both be R3. That doesn't happen in general. If t is onto, then the image will be all of R3. It equals R3 is the main point I'm trying to make. Here I'm saying R3 is a subset of itself. I didn't have to write that. But this is the main thing to focus on right here. We can also try to understand the action of t geometrically. Does it involve some sort of higher dimensional rotation or reflection? In general, that's quite difficult and not something we're really going to focus on for higher dimensional linear transformations. However, we will focus on something else that is related. What happens if we iterate t? In other words, can we understand solutions of the difference equation, not differential, x sub n plus 1, and that's a vector, equals t of x sub n, where n is 0, 1, 2, 3, etc. Difference equation, we haven't talked about that in a while, even in the differential equations part of this course, in a number of lectures. Remember, I also called this course Discrete and continuous dynamical systems is another name for the course. Continuous dynamical systems are differential equations and their solutions. Discrete ones are difference equations and their solutions and how they behave geometrically. We can iterate the function t by continually multiplying by the matrix A, meaning we're going to have to find powers of A. How do you find a power of a matrix? Do you just raise the entries to the same power? The answer is no, actually. That's not what happens. And that's a big theme in this course, too, is to figure out what happens when you raise a matrix to a power. And it's got to be a square matrix, by the way, same number of rows and columns to be able to do this iteration. In this case, the domain and codomain have to be the same dimension to be able to actually even do the iteration. That should make some intuitive sense if you think about it. How about for our example? Here's our example. What's the kernel? We need to solve the equation t of x equals 0, because we're trying to find the x's that give an output of 0. That's the kernel. We can do that by row reduction, except now the numbers to the right of the dashed line that I draw in here are a bunch of zeros, because it corresponds to the 0 vector. The right-hand sides of all the equations are all zeros. So I do the same row operations because I have the same part to the left of the dashed line to get it into reducer or echelon form, where I have leading ones along the main diagonal, zeros below them and zeros above them if I can. Same row operations as before, same things happen to the part to the left of the dashed line. The part to the right of the dashed line stays 0 the whole time. And I get into reducer or echelon form like this. Before I get to the punchline of describing the kernel, let me also say this row replacement operation is just one of 3 possible row operations. You can also swap rows, and you can also multiply any given row by a non-zero constant. This corresponds to, in parametric vector form, well, this corresponds to the equation x minus z equals 0 and y plus z equals 0, so that x equals z and y equals negative z, and z is itself, so I can write the kernel in parametric vector form as the set of all points or vectors z, negative z, z as z ranges over R. I can factor out the z and write that as z times the fixed vector 1, negative 1, 1 as z ranges over R. And think of that as a subset of the domain. And pretty obviously, I hope you look at that, if you translate this to thinking of it as a set of points, it's got to be a line through the origin in 3-dimensional space. Right? Because there's no constant vector that's being added here. Any multiple of this fixed vector, if I think of that fixed vector as having its tail at the origin, will give me scalar multiples of that, vectors that are the same direction or opposite direction with different lengths. And if I translate that to a set of points, I get a straight line through the origin, because the tail of the vector is at the origin. How about the image? Well, there's actually no work you need to do beyond what we've already done. And in fact, you can even use the original system effectively to describe the image. The image can be thought of as the set of all vectors or points, if you translate to points, that look like this, that match this. I also could have written it this way, or I could have written it this way. As x, y, and z range over the real numbers, and you want to think of this as a subset of the codomain. Again, the domain and codomain happen to be the same in this case. Not so obviously, this is actually a plane to the origin in 3-dimensional space. But wait a minute, there's 3 variables here, x, y, and z, that are free to vary independently of each other. Shouldn't this describe all of 3-dimensional space? That's why it's not so obvious that it's actually a plane, 2 dimensions. It does go through the origin for sure. When x, y, and z are all 0, you get the 0 vector, which can be thought of as the origin. But it turns out in this situation, this turns out to be a plane. I'm not going to explain why. All right, this is our last slide, I believe. Yeah. So this is going to be briefly talking about algebraic properties of vectors in three-dimensional space, or in fact, even in n-dimensional space, these properties hold. I've already mentioned these properties for two-dimensional vectors. They are worth emphasizing again, and it's worth me emphasizing certainly to my students, but in fact also to anybody out there. You really should try to remember the names of these things. It's really helpful, actually. And it's going to be beneficial later on when we talk about something called vector spaces, kind of an abstract idea. By the way, in lecture 9b, we're going to talk about other properties, actually, of three-dimensional vectors. Dot products, angles, and something called cross products. But these are the purely algebraic properties. Don't ignore these things. This is a big thing to remember. There's the associative property of addition. Doesn't matter where you put parentheses. U plus in parentheses V plus W, which by order of operations means do V plus W first, then add U, is the same as doing U plus V first and then adding W. And this is easy to verify component-wise based on component definition of vector addition, because it's true for each component. Real numbers satisfy the associative property when you add them. You want to assume you know everything about real numbers and then how to add them and multiply them when you prove these kinds of things. I'm not stating it here, but it's an unstated assumption that we're assuming, and we can in fact prove that this is true for all U, V, and W. If you make an upside down A like this, that means for all. Let me just write U, V, and W. I could write in R3, but I also could write in Rn. Maybe I will go ahead and write that in Rn. This upside down A means for all. It's just shorthand notation. Kind of fun shorthand notation for all. There's also shorthand notation for there exists. It's a backwards E. Oh, so much fun. That means there exists. But these equations that I'm showing you here are true for all vectors in Rn, where n is any positive integer. It's the associative property because you're associating in different ways and saying you get the same thing. There's the commutative property. What's commuting? It's moving back and forth. It doesn't matter where you put the vectors with respect to addition. V plus W equals W plus V for all V and W in Rn. I'm not going to bother writing it. Also could have done U plus V equals V plus U. The symbols themselves don't matter. The zero vector, whose components are all zero and which is visualized as a dot at the origin, is the additive identity. You add it to any vector, you get that vector back. And it doesn't matter what order because of the commutative property. I could have just written one of these actually because I'm assuming, or I know the commutative property is true. Opposites of vectors are additive inverses. What's an opposite? It's when you multiply a vector times -1 to get negative V. V minus V, which by definition is V plus negative V, or negative V plus V equals 0. Negative V is the additive inverse of V. You add it to V, you get 0. These are similar to properties for numbers in regular real number addition. But it's so important to keep track of what's a scalar and what's a vector. That's so important, and I want my students to draw little half arrows or something above their vectors. Because if you don't, it gets you confused. This is for your benefit. There's an associative property of scalar multiplication. Doesn't matter whether you put the parentheses here or here. This means take lambda1 times lambda2 first, then multiply by V. This is a product of numbers. This number times this vector is a scalar multiplication of a number times a vector. Here, we do this multiplication first. This scalar times this vector. That's a scalar multiplication. That gives me a vector. This scalar times that vector is another scalar multiplication. So the operations are the same. This particular product is the only one that is that product of numbers. Distributive property 1 says you can distribute scalars through vector addition like this. Distributive property 2 says you can distribute vectors through scalar addition like this. And you could also do it the opposite order, though we usually put our scalars in front of vectors rather than behind. And that's just a convention. The number 1 is what you might call a scalar multiplicative identity. 1 times any vector is the vector. The number 0, that's the number 0, not the vector 0. Though I did mention you can think of numbers as vectors, one-dimensional vectors. But, okay, don't worry about that. The number 0 is an annihilator. What does that mean? It multiplied times any vector, you get the 0 vector. Notice this is the number 0, this is the 0 vector, because it's bold-faced. Here's a point where you want to keep track of what's a number and what's a vector. So multiplying by the scalar 0 annihilates v, makes it become 0, so to speak. That's just pretend in your mind, in your imagination. And that is the end of lecture 8b. Thanks for watching.